Okay, so let's start today with something that we studied in the last class, the HMAC, authenticate. Then we'll study authentication encryption, authenticated encryption, and EAD. Okay, so these are the contents. Okay, please go through these contents also, because you will learn a lot by going through these. We'll mute all of you. Okay, all right. Okay. Now, I'm sure you have developed the security mindset by now, but this is, of course, very simple message. Can you tell me what is the message here? Yeah, anyone? There's some message here, right? Message here is don't copy your assignments from others. You'll get 0 marks or fail marks, right? Okay, all right. Okay, so this is where we are in cryptography roadmap. We have already covered these parts. Started with one-time pad, then we studied symmetric key encryptions, various ciphers, block ciphers, and various modes. So we have completed discussion on confidentiality from symmetric key perspective. Now we are looking at these two aspects, integrity and authentication, and we started with simple MAC, which is, and before that we have studied hash function. Intelligent use of hash function gives you also integrity checks, like we download a file from website, etc., and then we can check whether hash matches with that or not. So it does not use the key, but we have seen if we don't use key to have some kind of checks at both ends, sender and receiver, that is between Alice and Bob, all, and condition is that this symmetric key only Alice and Bob know, then we can find it out whether the received message and corresponding tag is appropriate or not by recalculating tag and matching it with received tag. As simple as that, right? So we'll repeat HMAC, then we'll look at authenticated encryption, and then AED, and then a need for random number generator. Okay. Now this we already studied that HMAC has proven to be secure. And the basic idea is that key is hashed together with message. Now look, in symmetric key encryption like AES and DS, we have a key at receiver and sender end, and what we do is that we encrypt the original message using this key and get the ciphertext. We send the ciphertext to the other end and use the decryption key, same key for decryption, and get the original content back. Okay, now encryption and decryption is time consuming. As you have seen in case of AES and DES, how many stages of transformation it requires. Okay, now here in HMAC, although we want to have integrity check, but what we are going to do is that we are not going to use encryption, but use the key somehow. Okay. So see, along with, say for example, in MAC, what are we doing? We are sending, let's assume this message M, and then we are generating a tag using key over message M and sending both tag and message, right, to other end. Another end also calculates, receives this message, uses the key and calculates the tag and if tag matches with receive tag, we say everything is okay. All right, but here we are just using the key, but we are not encrypting. Remember this thing, right? But if we simply hash the key along with if we just concatenate or just add the key, concatenation is nothing but take one string, add to that another string, that's called concatenation. If we concatenate and then send it, then it's not nice method. So we'll have to do some transformation in with the key and use a message appropriately so that it's secure. Okay, so we have seen this method, and now we are going note that if message and tag is of same size, then and the message is say 100 megabytes, this will be 100 megabytes. This is not efficient mechanism, right? So we always say the tag has to be smaller, say something like 256 bits or 512 bits or something like that, whatever be size of message. So then we use the property of hash. Okay, so what we do is that we take this message and use some kind of hashing mechanism, then you get a tag of smaller size and do some kind of transformation with the help of key. There's a basic method, right? Okay, all right. So the advantage of HMAC is that H stands for hash and MAC. Combining hash and MAC, this advantage is that we use available hash functions. So you already hash function library is available, right? If you go to, for example, OpenSSL library, then there is you will find large number of functions for hashing. Okay, and then if you change one hash with other hash, that's allowed. Okay, and then it preserve the original performance of hash function. Hash functions are very fast, so creating HMAC from that will also be fast, and this also handles key in very simple way. Okay, all right. And then we have seen HMAC details. Now we have one key here and message M, and from that basically we have message M, and then we have to get from this a tag which is HMAC tag. Okay, now for that we'll have to use a key K to create this tag. So do some transformation on message and get a digest of that, which is that uses key K. Okay, all right. Okay, now the first transformation we do is that once we get the key K, which is randomly generated, okay, then if the key is very long, then we bring it to the proper size that is required, and we get from this key K we get a key called K dash by appending zeros or reducing the size by hashing it. Okay, so received key we call it K dash because K dash has to be size of hash output. So hash output here, for example, is 256 bits. Then this key is also reduced to 256 bits. Okay, or increase it length. If it's smaller key size, then increase the length. Any question up to this point? What are you trying to do? Now, whole aim is that somehow get an integrity check and what? And authentication. Authentication means that it is only Alice who has sent the message to Bob. When Bob is certain that it's only Alice, then we say it's authenticated. Integrity means that somebody in between has not tampered with the message. Okay, now what this transformation we do, the crux is here. So we have already got new key K dash from original key K. The first function we do is that use the hash function, whatever we have studied, right? Like AES and For example, we are using AES. Okay, so this hash function is this function that we run, and in that there are two inputs. Okay, first is the key, let's call k double dash, and the message, right? So here this becomes the key, modified key, say k double dash, and this is a message. I'm sorry, okay, all right. Okay, so now what we do is that we here concatenate, this symbol represent concatenation. So now note that we are not doing encryption, so we take this modified key, which is nothing but k dash exclusive or with iPad. So we are not using k original key as it is, but we are changing its form using some patterns. Okay, and so that key k dash exclusive or iPad, you get it by exclusive of, let's assume this is k double dash, then concatenate it or add to that message m. Okay, all right, and run this over hash function. Okay, all right, so you get out of this say 256 bits output. Let's assume hash function gives you 256 bits output, and then you add to this, concatenate it with this key, modified key, say let's call it k triple dash, and then whatever string we get, run this over hash function. Okay, so that's the theory. All right, so we'll skip this because we already discussed this. So the math, what we do is here, this is a k dash or k, let's assume k dash is same as k, by adding few 0 bits, some number of zeros and etc etc. Let's not worry about it. This, let's assume there's original key k, exclusive or it with this pattern 36363636. Okay, and of course these are in hex. Okay, and then we get this string. Okay, now join this with message m, this called concatenation, and then hash this, you get this string here. Okay, now this is the first phase. Second phase is that take the same key k, exclusive or with opad, which is 5c 5c 5c. Now note that here the key that we have got after this operation has to be different from the key that we got here. That's the whole objective. So this part must be must have transformation with different key. So now what we get here is k exclusive or with opad. Now we now concatenate these two things, something that we received from first phase, that's here, and this modified key, and then again run a hash function. What we get is HMAC. Okay, please go through the PPTs, you will understand it. Now what is the idea of HMAC? Now HMAC, we are not sending it alone, because one way we cannot, from HMAC you cannot derive M. This is not possible, right? It's not inverse function, because we are using hash. Hash is always one way function, you know that, right? We are not encrypting, we are just using adding the key. So if this is HMAC or tag that you receive, from this you can't get M. It should be clear, right? Okay, so what we are going to send, we are sending M, or when Alice sends something to Bob, she sends M, and then she sends HMAC, this tag that you receive generated using the key K, that is to be sent. Our key has already been transmitted to, securely transmitted to Bob. Okay, Bob would receive this, okay, and use the same function that we have here, HMAC function, and generate using this message M and key K. The input is H, message M and key K. From that it generates a tag. If the tag matches with the tag received, then everything is fine. Else somebody has modified the message. All right. Okay. Any question? Please go through previous PPTs. I will also upload videos, because if you miss one lecture, it is becoming very hard to understand other next lecture. Okay. So properties of MACs is a cryptographic checksum. A symmetric, we are still in symmetric key methodology. We can use any input. Input can be of any size. Okay. But output is always fixed, and it preserves integrity, because if somebody has tampered with the message, say Mallory for example, then she cannot generate the tag because she doesn't have the key. Key is only with Bob and Alice. So this also, it gives authentication, because it's only Bob, it's only Alice who has generated the message properly, right? Because she has the key. Sorry, who has generated the tag properly, or cryptographic checksum properly. But we still don't have non-repudiation, because symmetric keys don't provide non-repudiation, because both Alice and Bob can cheat each other. There's nothing that can be proven that Alice has sent that I will give you $100. Bob can say that you have sent me a message of $1,000. You committed 1,000. So there is no way anybody can prove that who's telling lie. Okay. Do Max give confidentiality? No. Because first thing is that we are sending message M as it is, right? So there is no confidentiality. And Macs are also deterministic. So there are no IND CPS security. The tag that you generate, or HMAC or MAC, whatever, of key K and M, these are deterministic. Okay. But is sufficient for most of the applications. Okay. So HMAC is a popular MAC, and there are other types of MACs also. We have studied just one of the many. What can be one example, one use, which is very simple use of MAC? Suppose your laptop is hacked. Okay, so virus has infected some of the files. This is very common scenario, right? So, and before that, when everything is good, then you have multiple files, say F1 to F1, and then you create MAC of each file. Now you derive the key using your password. So this algorithm takes your password and derives the key, use the key over the file, which is M, and generate MAC, and then store it somewhere which is very secure, maybe in the cloud or somewhere, right? Okay. Now virus comes or malware comes and infected some of your files. How do you know which files have been infected? You do this operation, again calculate MAC, you get some MAC value, say M dash, which will not match with the stored value of MAC, and then you will come to know about the files that have been corrupted. Okay. Any question up to this point? I mean, are you able to understand? I think it's need for you to take, spend some time and understand what has been taught. For that, you need to please go to PPTs all over again, read from the book, number of books, number of video lectures. And I think we should take a test now, because this will help you in learning. Okay. Any question? So where we are now? We started with symmetric key encryption. This diagram you would have seen at least n times. We take a plain text, we use the key, we use encryption algorithm AES/DES or whatever you want, or many others. You get, based on this encryption function, get ciphertext that's sent over insecure channel, it reaches to other end. Use the key, same key which has been communicated between Alice and Bob. Use it for decryption, you get the plain text. Very simple, right? In between, nobody can, because this ciphertext is based on the key, and key is known only to Alice and Bob. Mallory or Eve in between cannot see what is being sent. So what do we achieve out of this? Anyone, please answer. Please attempt at least, right?
Confidentiality.
Very good. We have achieved confidentiality. What's your name?
Ayush.
Yes, Piyush. Thank you very much. But we have not achieved confidentiality. Yes, integrity no, authentication no, non-replication no. So this is where we started with. Okay. Why integrity no? We can do Mallory can do man in the middle attack, because you know what we are sending is only encrypted version of M that uses key K, and Mallory simply changes whatever she wants to. You know, she changes to M dash, generate something, and uses some key K dash and create text and sends it to the other end, and Bob will never come to know that something has changed. So it means that it does not have integrity and also authentication, non-repetition anyway, because symmetric key type, so we cannot have non-repetition. Now we have moved from that to cryptographic hash functions, which is nothing but we take a message M and do transformation that we have seen and create a small hash of that. We call it small z or whatever, h of M. It's just one way function, that's it. We don't use key here. Okay, all right. So now with M, now since it's a one way function, you cannot send this tag alone or z alone. So it's a, so basically you'll have to send M and also along with this h of M. Okay, so it means that now there is no confidentiality because Mallory in between can see M. Okay, and integrity, you can say in some cases yes, but Mallory can always change M to M dash and then HM to HM dash. So nobody will be, or Bob will not be able to come to know about it, right? So it means that MITM, man in the middle attack, is possible. But if you have filed somewhere in website and you download it and then check you know whether it matches with the published hash, then you are fine. So in limited case, yes, it's possible. Okay, then we came to the MAC. What we do here in MAC, we have a message M which Alice generates, and then she generates a key K which is a random key. Okay, and this key is sent to other side properly, securely. Okay, so we cannot doubt that Bob has different key. We'll say Bob will have the same key, but how this is transmitted, that we'll study later. And she uses this key over message to create a tag or a small tag here that has a component of the key, or that is transformed using key. So message, so basically tag is generated using key K over message M in very intelligent way, and that of course we use here hash for efficiency. Okay, we are not using encryption here, and then we send message and the tag both. So now note that message will go as it is to other end, and then that will be applied over the same function, MAC function, and then new tag is generated, T dash, and that T dash matches with the received tag, then we say everything is great, good, otherwise not. So what? We have achieved what? Integrity and authenticity, but message is sent in plain, such that other party can apply same function. So it means that it's visible to all. So confidentiality, no. Non-repetition, no. Because same key is being used by Alice and Bob, anyone can cheat. Okay, all right. So now we are searching for a scheme that can provide confidentiality, integrity. When we say integrity, it also means authentication. In general, in literature, you will not find these words separately. Integrity, of course, includes integrity plus authentication, but nevertheless, we can say confidential integrity and authentication. And that method is called authenticated encryption. Now, what we need to do as a common sense? Anyone? Integrity and authentication, we have already achieved MAC. So we'll have to use MAC. Now, confidentiality, how can we achieve? Is only by encryption. So we'll have to combine what? Encryption methodology with MAC, message authentication code. We'll get a new scheme. So now you take a message M, okay, and now you have various ways of doing it, right? From you encrypt this using some key K, okay, and you get encryption of message M using key K. Now this key is to be sent to other side to Bob, okay. So the Bob can decrypt. So we achieve confidentiality. Now along with this, Alice can also generate MAC and attach. And now MAC, using MAC, she has got to have a key, and this key has to be different. Otherwise, the whole scheme will fail. Okay, and attached to this even this encryption, this MAC, and send it to other side. The Bob will receive encryption of the original message and will get MAC that uses M and some key K dash. It means now in order to Bob to decrypt, Bob should have key K, and in order to find out if the MAC matches, Bob should also have key K dash. Okay, so this is very simple scheme. We have done it, right? Is it okay? Will it work? Hello.
Sir, it should work, but I think it will be slow.
Yeah. Of course, encryption is there, then it has to be slow. But encryption, note that encryption is the only way to provide confidentiality. See, even now, whatever we are talking, whatever I'm showing you is going over encrypted channels, right? So all our data is encrypted over WhatsApp or even WebEx or whatever. We are using encryption. So now there are ways of doing it faster, right? So there are faster algorithms are available. Not necessarily we are doing AES, DES all the time. Maybe something more. Like here, we may not be doing AES, DES. In streaming, when we are streaming data, then we are doing some other kind of encryption. Okay, but it will work. Okay, all right. So now we want to achieve all these three that we have studied. Okay, now there may be some, some way or other we may have to compromise little bit authenticity depending on threat model, but in general we should come out with schemes. So first scheme is something that we already discussed, that encrypt and MAC. Second is encrypt then MAC, and third is MAC then encrypt. What operation you are doing first? That's the essence here, right? Encrypt in MAC, you are doing something that we have studied just now. Encrypt that MAC, that you take message M. Okay, this is a message M, and of course you are using key K. Sorry, this message M, you use encryption. The encryption function over M using key K. Okay, you get, of course, this encryption function, so you get same thing here. So this encryption function, what you get is M dash, which is equal to E M of K. Now, one simple thing is that, as we discuss here, you create a MAC based on message, right? Second method would be, you have done encryption, then use this and get MAC over this, something that has been encrypted, because size is the same here, right? This M and M dash size is same, and then you use MAC of this M dash using key, different key here. Let's say this first key is K1, then second key will be K2. Okay, and then send it this to Bob. Now in between, Mallory receives this. Since she does not have key, either key K1 or K2, she will not be able to tamper with it. And if she tampers something, then it will be known, because the tag will not match. Okay, and third is that MAC then encrypt. You take message M, and then you have generated tag from this one, or MAC, and then, so here use MAC function to generate using K, say K2, and then the whole thing use encryption using K key1. Okay, this is encryption that has input to this M concatenation with MAC using key K1, and then whatever output you get, M dash or whatever, you just send it to Bob. So these are three methods, right? So we'll look at one by one again. First is encrypt and MAC. You have message M, you encrypt this using K key1. Okay, you get ciphertext here. Take the message again and get hash function, MAC function, MAC output of that using key K2. This is key K2, and attach these two or concurrent these two and send it to the other side. Okay, all right. Okay, so now you go through this, very simple. Okay, so only issue here is that confidence. See, it is not IND CPA secure. What? Now here C will be IND CPA secure because you may be using one of those modes. Okay, we have seen modes of operation. Okay, if you use proper mode, okay, CBC for example, then this is IND CPA secure, but MAC is not. Because MAC function we are not doing CPC mode of operation there. We are simply using HMAC and using the key and message M. So this is not IND CPA secure. So it may leak some info. If Mallory in between looks at C and MAC of M1, and if she is able to force Alice to send this over text of her liking, then if she observes MAC of whatever she receives, she can get some info, but for most operations this is okay. All right. The second scheme is take message M, which is called encrypt then MAC, then encrypt it using key K1. The output is ciphertext, and take this encrypted output for the MAC. Okay, so the MAC that you are running here should have output of this encryption function. That's a encryption of message M, which is C, and use the key K2, and you get, since you are using HMAC, you'll get a small tag here, and you attach this and send it to other end. Okay, so integrity yes, confidentiality is also yes, but MAC, again, this MAC that we are generating here might leak some info. Okay, but that's fine. All right, so these three things again, just a minute. Or did I go wrong? No, it's okay. Okay, something. All right, so this was the second scheme, and third scheme is that you get a MAC, take message M, get a MAC from this one, and just encrypt it and send it. All right, this is called MAC then encrypt. First you MAC, then encrypt and send this as it is. Now you have to, if Alice is doing this, then she has to send two keys K1 and K2. K1 is for encryption, K2 is for MAC. And what we achieve is integrity and confidentiality, yes. All right. Same thing that we have shown earlier is discussed, so we will not go through these slides. Okay, all right. So which method is best? Encrypt and then MAC, this method is preferred. Then MAC, then encrypt. Okay, so basically what are we doing? This method will prefer. Then the other method. Then this method. Although all these methods are being used, both three methods are used in practice. But the question is that why encrypt then MAC is better than MAC then encrypt? Simple reason you can say is that what Bob receives is, some encryption of message M and MAC. Okay, and then first he has to decrypt it, then get message and get MAC. So it basically, and from that he has to generate another tag or calculate MAC again, and then find out if something is tampered or not. So it means that you don't know if tampering occurred until you have decrypted the whole message. So basically it will be little slower. And of course side channel attacks are possible. We will not discuss this point. Side channel attacks are essentially implementation based attacks. Okay, so these are the three methods that we have seen earlier. First is encrypt and MAC. Okay, you take message M, you encrypt this using key K1 or KE, whatever, and then this encryption is here, and then you calculate the MAC from original message M and attach here and then send it to the other end. Second method we have studied is encrypt then MAC. First you encrypt the message. Okay. Oh, sorry, MAC then encrypt. So you get, I'm sorry, take message M, get in MAC of that, and then encrypt the whole thing. This encryption. And something that we like or most efficient is encrypt and encrypt then MAC. First take message M, you do encryption of that using key K1. Okay. Okay, and then take this whole encrypted message and get MAC of that using different keys, say K2. Okay, all right. The usage are simplest one, encrypt and MAC in SSH protocol. MAC and encrypt is used in SSL protocol, and most popular, which is IPsec, uses encrypt then MAC. Okay, all right. So to summarize, we have already studied just now 3 methods: encrypt and MAC, encrypt plus MAC, we can say encrypt and MAC. So basically take the same message, do encryption, and same message you do MAC, attach these two and then send it to the other end. Second is MAC then encrypt. So the sequence here is that take message M, get encryption MAC of that, MAC of M, and then encrypt the whole thing. And third is encrypt then MAC. Okay, all right. So basically take message M, encrypt it, and then get MAC of encryption of the message. Okay. All right. Any question? Very quickly we'll finish the next topic, which is AEAD, authenticated encryption with additional data. Note that when you are creating IP packet, what fields it has? It has a data, right? Of course, that's most important, payload or data. But how will the data go? You have to have source IP address, minimal I am telling you. And most important is destination IP address. Like in envelope that you send it to your parents, you have something important is a letter inside, but on top you write, you write address, right? So same thing, source IP and destination IP. Now how do you do encryption over this? If you encrypt the whole damn thing, you encrypt this packet, and it goes to a router in between, how will it know where to send it to? You mean to say if you are using key1, you will send this key to everyone? How do you know the router software does not have mallory sitting there? Okay, it means that we cannot encrypt everything in real life. Okay, so what we can do is that we can have, of course, confidentiality and integrity over plain text, but only integrity over additional data, which is nothing but IP addresses. Okay, so if assuming that this is your IP address part or header part, header for a packet, and this is actual content, that's IP packet contents, right? So you can encrypt this, and you can also do basically integrity over this. So you can have mechanism for encryption and integrity, but this has to be associated data like IP address has to go naked as it is in a plain text. But what you do is that you calculate, say for example, HMAC of this, okay, and then send it along with, attach it to the packet, and or it may be part of the packet, or maybe part of something, and send it. Okay, so other end at least we'll know whether IP address part has been changed or not, or header part has been changed or not. So that level of integrity we can check, but there is no confidentiality in associated data. So that's the message. Okay. Last 5 minutes. So all throughout, when we say key, Alice is generating a key for encryption or generating key for authentication, like in case of MAC or HMAC. Symmetric encryption, right? That we have studied, AES or DES. What is the assumption? What is the assumption about the key? So let's assume that Alice and Bob are communicating with each other for small period of time. Okay, so Alice will generate key and she will send it to Bob securely. Question is that how this key is generated, and every time she is going to use the same key? No, the key is very similar to what we have used, seen in case of password, which is there is a password space. So key is usually we have seen of certain size. Okay, 512 bits or 2 times 512 is 1024 bits. So how is she going to generate this? If there is a pattern in this that she is generating, then in between Mallory can easily find out what is going wrong. She can always generate the key and then game is over. So this key that Alice is generating has to be absolutely random in nature. Okay, now the question I will ask now to you is that on computer, how can you generate a random key? Everything in computers is deterministic, right? Same algorithm runs. As many times you run, so you give same input, you get same output. So how do you generate a random number in a computer or on your laptop? Please answer this. Hello. Okay, so there's a challenge. How to generate random number in computer? So we use the word pseudo. In Hindi, is equivalent is nakli. Okay, something that appears as a random number, we can of course generate in computer using some smart techniques. This is called pseudo random number. Okay, please go through this cartoon. So this has a message here. Randomness in life, science tells us the world is fundamentally random. So events in our lives are also random. Okay, what is the probability, like your father married to your mother? How did this marriage happen? Maybe some, father's friend met somebody and who said there is a, possible match, and then he met your mother and done. Okay. Or for example, you get a job. I mean, if you don't know even about the job and someone tells you that there is a job, why don't you apply, and you get it? Or somebody goes on a road and then suddenly this road is all empty, suddenly something appears from the other direction and the accident happens. A lot of things in life are random. Okay, and please go read this book if you have time sometimes. It's a nice book. Okay, all right. So it says that something happened in your life. For example, you get something, one lottery. You buy a lottery ticket and you get output from that. Means that you won the lottery. But that's just by chance. Don't keep buying lottery thinking that I am too lucky and I will always win it. Okay. So randomness is very, very important in symmetric key encryption. Okay, for example, we use the key for encryption, right? The encryption key. We use nonce or random IV, initial vector, right? Okay. So so many places we do, and if the attacker can predict a random number, then of course the whole crypto system will fail. The question is that how do we generate random numbers then, right? Okay. So basically when we say random and unpredictable. Okay. And then you would have heard this called entropy, which is nothing but measure of uncertainty. So we'll look at this concept in the next class. Okay, because there is nothing truly random number in computer. Now you'll have to look at the sources of truly random number, like heat generated in your laptop, or your some of these things which are analog in nature mainly, or your movement of your hand, for example, mouse movement that you do is not deterministic, it's all random, and we look at in terms of nanoseconds, right? So what we do is that we take two randomness sources and take this input to an algorithm, because there is a randomness here, true randomness, and then you generate output like this. We call it seed. This is two random source, and then you have program, and it generates seemingly random or pseudo random output. So we will study this in the next class. All right, any question? All right, then see you tomorrow.
Hello, sir.
Yeah.
Sir, I have a
Yeah.
doubt in assignment, sir.
Yeah, just a minute. Just hold on for a minute.
Okay.
Just hold on for a minute. Yeah.